300 million years ago, Earth enters a strange and humid chapter in its history. Vast coal forests stretch across the continents, and endless swamps breathe out thick, oxygen-rich air. Giant dragonflies patrol the skies, armored millipedes roam the forest floor, and early amphibians slip between water and land in a world without flowering plants or dinosaurs. Today we travel back to the Carboniferous to explore how this age of giant creatures and silent dark swamps reshaped the planet. If you enjoy journeys into deep time, please like, subscribe and share, and tell us in the comments which Carboniferous creature or landscape would you most want to see with your own eyes. Thank you for watching. Now let's begin. The early Carboniferous Earth is a planet in the midst of long-term tectonic reorganization. It lies within the Paleozoic era in the interval just after the end of the Devonian and before the later stages of the Carboniferous that lead toward the Permian. The solid outer shell of the planet is divided into moving plates, and their slow motions bring scattered continental blocks into new patterns. One group of plates carries the large southern continent known as Gondwana, which occupies high southern latitudes and extends over the region of the South Pole. Another group carries Laurussia, a composite landmass formed from collisions during earlier periods, which lies near the equator, or slightly to its south, and gradually drifts northward through Carboniferous time. Farther north lie continental blocks such as Siberia and smaller terrains, while to the east of Laurussia and Gondwana there are blocks that make up what later workers call the Asian landmasses. These land areas are arranged in a broad arc around an ocean known as the Paleotethys, and beyond them to the west and north lies the immense Panthalassic Ocean that covers much of the planet. The spatial pattern of land and sea is therefore not random. Instead, a near-continuous chain of continental crust defines a ring around an equatorial to mid-latitude ocean basin, while a single great ocean covers most of the remaining surface. Where Gondwana approaches Laurussia, compression occurs and a long mountain belt begins to rise. This belt, formed through processes that later geology groups under names such as the Variscan Alleghenian and Ouachita orogenes, stretches thousands of kilometers along the collision zone. It links uplifts in regions that now correspond to parts of North America and Western and Central Europe. Within the early Carboniferous, it is not yet at its greatest height, but active deformation, magmatism and uplift are already shaping wide areas along the convergent margins. To the east and northeast, additional mountain building takes place where smaller terrains and microcontinents interact with Siberia and with the older continental core of Laurussia, including the early stages of the Uralian orogeny. These high-standing regions influence erosion sediment supply and the locations of subsiding basins around their flanks. Surrounding the continental blocks, the seafloor spreads and subducts along long oceanic ridges and trenches. In the Panthalassic Ocean, mid-ocean ridges stand as broad elevated belts, while in the Paleotethys and smaller marginal basins subduction zones consume oceanic crust. The distribution of these spreading centers and subduction belts controls seafloor age ocean depth and the pattern of deep currents that move heat and dissolved substances between equatorial and polar regions. Over geological time, the balance between ridge length spreading rate and subduction affects global sea level by changing the volume of ocean basins. In the early Carboniferous, relative sea level is generally high compared with many later intervals, so that wide areas of the low-lying continental interiors are flooded by shallow epicontinental seas. Around the equatorial margins of Laurussia, clear warm water covers broad continental shelves where carbonate sediments accumulate. These shelves grade seaward into deeper basins of the Paleotethys and Panthalassic Oceans, while landward they pass into low-relief coastal plains and river deltas. Along the southern margins of Laurussia and the northern edges of Gondwana, convergent plate boundaries produce foreland basins that subside under the load of growing mountain chains. These basins fill with thick successions of marine and marginal marine sediments, delivered by rivers draining the rising highlands. In the earliest Carboniferous, these basins are dominated by marine deposits and by siliciclastic sediments, eroded from nearby uplifts, recording sustained interaction between rising highlands and subsiding lowlands along the collision zones. On Gondwana itself, the situation is different between low and high latitudes. Parts of the northern margin of this large continent occupy temperate to subtropical latitudes and face the Paleotethys or other marginal seas where rivers deliver sediment to coastal plains and shelves. Farther south, large areas extend into high latitude and polar regions where long-term cooling that began earlier in the Paleozoic promotes the growth of ice sheets. The presence of ice on land alters patterns of erosion and sedimentation, delivering glacial deposits to some marine basins at the fringes of the continent. The combination of high southern continental elevations ice-covered surfaces in some regions and lower latitude lowlands on the same landmass introduces strong contrasts in the physical landscape of Gondwana. When the early Carboniferous Earth is viewed at the scale of the whole planet, several organizing features stand out. A ring of continents partly encircles the Paleotethys Ocean. Near low latitudes, a single immense panthalassic ocean occupies most of the globe, and a large southern supercontinent extends across the high latitudes with areas of ice cover. Within this framework, mountain belts rise along convergent margins, and broad, shallow seas spread across many low-lying continental interiors. Subtle changes in relative sea level, driven by both tectonic and glacial processes, repeatedly shift shorelines landward or seaward over spans of millions of years, altering the width of shelves and the area of flooded lowlands. On many of the equatorial shelves, carbonate platforms several tens of meters thick accumulate over time, recording stable warm water conditions and low rates of terrigenous sediment input. In other regions, especially adjacent to rising mountain belts, mixed carbonate and siliciclastic successions develop as pulses of sand and mud dilute carbonate production. These large-scale patterns of land distribution, mountain elevation, basin subsidence, and shallow seas set the physical context in which atmosphere, climate, and surface environments operate during the early Carboniferous. They determine where moisture-bearing winds rise, where rain falls most persistently, and where rivers, deltas, and coastal wetlands can exist, while the detailed behavior of air masses and temperature gradients belongs to the atmospheric and climatic system rather than to the solid Earth pattern described here. At the scale of continents and major basins, the early Carboniferous Earth system therefore consists of interacting solid Earth and ocean components that create a distinctive and internally consistent pattern of land and sea, a pattern that governs the distribution of shallow seas, carbonate platforms, clastic wedges, and continental interiors preserved from this interval. The early Carboniferous atmosphere and climate operate within the constraints imposed by the distribution of land and sea, the presence of polar ice on Gondwana, and the activity of extensive vegetation on the continents. The composition of the air differs from that of earlier Paleozoic time because land plants with well-developed conducting tissues and roots now occupy large areas of low-latitude land. Their growth and decay alter the balance between oxygen and carbon dioxide over spans of millions of years. Geochemical models and proxy data indicate that atmospheric oxygen in the early Carboniferous is already elevated compared with some earlier intervals, probably not far from or slightly above modern values, while carbon dioxide is relatively low for a greenhouse gas that plays a central role in controlling surface temperature. The exact percentages are uncertain and vary between reconstructions, but the general pattern of rising oxygen and reduced carbon dioxide during this period is robust. This combination places the planet in a long-lived ice age state centered on the southern supercontinent, on the high-latitude parts of Gondwana, where the landmass extends across polar and subpolar zones. Large ice sheets and valley glaciers occupy uplands and broad plateaus. They thicken and thin over time in response to slow changes in orbital parameters, sea level, and greenhouse gas concentrations, and they discharge ice into surrounding seas. The existence of these ice masses means that mean annual temperatures over much of the southern high latitudes remain at or below freezing, with strong seasonality in incoming solar radiation and in snowfall. In contrast, the low-latitude regions around the equator experience warm to hot conditions throughout the year, with little annual variation in solar input. The temperature difference between equator and pole drives strong atmospheric circulation cells in both hemispheres. Rising air near the equator and sinking air in the subtropics organize global wind belts, and the position of the intertropical convergence zone fluctuates around the equatorial band following patterns of maximum heating over the oceans and continents. Over the equatorial parts of Russia and the northern margins of Gondwana, where shallow seas, coastal plains and lowlands are present, this circulation brings frequent convection and heavy rainfall. Moisture-laden winds blow in from the Panthalastic Ocean, and the Paleotethys rise over warm surfaces and release water as intense showers and longer periods of rain. The result is a broad tropical belt that is persistently humid, with short breaks in rainfall rather than extended dry seasons. In such settings, high evaporation from warm seas and dense vegetation maintains a thick column of water vapor in the lower atmosphere. This water vapor is itself a powerful greenhouse gas amplifying regional warmth, even in a world with reduced carbon dioxide. At mid-latitudes on both sides of the equator, the climate shows stronger seasonality. In some regions, especially on the flanks of growing mountain belts, orographic lifting of air enhances rainfall on windward slopes, while leeward areas receive less precipitation and develop drier conditions. Interior parts of large continents, particularly within Gondwana, can be relatively dry, despite the global greenhouse gas configuration, because moist maritime air loses much of its water before it reaches the continental interior. These areas experience greater annual temperature range with hotter summers and colder winters than coastal zones at similar latitudes. The presence of extensive ice on southern Gondwana affects global sea level. When ice sheets expand, water is transferred from the oceans to land, and global sea level falls by tens of meters. When ice sheets retreat, meltwater returns to the oceans and sea level rises. Over early Carboniferous time, repeated advance and retreat cycles occur, driven by slow variations in orbital forcing and in carbon dioxide levels. These cycles produce alternating intervals when shallow epicontinental seas transgress onto lowlands, and intervals when shorelines retreat, exposing wide coastal plains. From the perspective of climate, these sea level changes alter the extent of warm, shallow water surfaces that release moisture to the atmosphere, and they also change the thermal inertia of the climate system by varying the area of water versus land at low latitudes. The chemical composition of the atmosphere is further influenced by interactions between plant soils and weathering processes. High rainfall in tropical regions promotes intense chemical weathering of silicate rocks, a process that consumes carbon dioxide and delivers dissolved ions to the oceans. Burial of organic matter in sediments removes additional carbon from the atmosphere-ocean system and contributes to the progressive buildup of oxygen. In the early Carboniferous, thick accumulations of organic material are beginning to form in some low-latitude basins. although the most extensive coal-forming intervals belong to slightly later stages of the period. Even at this stage, feedbacks between vegetation weathering and atmospheric gases are active. As oxygen levels rise and remain elevated for long times, the flammability of surface ecosystems changes. Experimental and modelling work on analogous conditions suggests that once oxygen exceeds a certain threshold, natural fires become easier to ignite and to sustain in dry intervals. In the early Carboniferous, many wet tropical regions are too moist to burn frequently, but drier uplands and seasonally dry lowlands can support fires that influence vegetation patterns and nutrient cycling. Cloud cover, storminess, and regional wind patterns reflect the combined influence of continental layout, sea surface conditions, and atmospheric composition. Strong latitudinal temperature gradients between the equator and the glaciated pole maintain vigorous westerly winds in mid-latitudes and encourage the development of storm tracks around the margins of the supercontinent. In some areas, seasonal shifts in temperature and pressure give rise to monsoon-like circulation, with onshore winds and heavy summer rainfall alternating with offshore flow and drier winters. In the early Carboniferous, warm tropical seas occupy a wide belt around the equator, where La Russia and the northern margins of Gondwana lie at low latitudes and are partly submerged by shallow water. These seas spread far inland onto continental crust, forming epicontinental seas that are generally no more than a few tens of meters deep, and that rest directly on broad continental shelves. The water above these shelves is clear and well lit, because most of the sediment supply consists of carbonate grains produced within the sea itself, rather than large volumes of mud and sand from distant rivers. Sunlight penetrates through much of the water column, allowing photosynthetic algae and symbiotic microorganisms to thrive on the sea floor and on the skeletons of invertebrates. Temperatures in these low-latitude surface waters remain in a warm range throughout the year, with only modest seasonal variation, and salinity stays close to that of normal marine water in most areas, because high rates of evaporation are balanced by rainfall and inflow from adjacent open oceans. Within this tropical belt, the Panthalassic Ocean and the Paleotethys feed water onto the shelves through broad, gently sloping ramps along continental margins. In some regions, the transition from open ocean to inner shelf is gradual, with a wide zone where wave and storm processes rework carbonate sand and skeletal debris into shoals, sand bodies, and banks. In other regions, especially where tectonic subsidence creates deeper marginal basins, the shelf edge is more pronounced and marks a clearer boundary between well-lit platforms and darker, cooler slope environments. Across many of these shelves, the dominant sediment factory is a community of sessile and slow-moving invertebrates, adapted to stable, firm seafloors in moving water. Crinoids, which are echinoderms with stalks anchoring them to the substrate, and feathery arms raised into the current, form dense meadows over large areas. Their calcareous skeletons break apart after death into grains that accumulate as crinoidal sand and gravel. Brachiopods attach to firm surfaces or rest on the sediment filtering particles from the water, while rugose and tabulate corals, bryozoans, and calcareous algae occupy spaces where light water motion and substrate conditions suit them. Together, these organisms create a patchwork of skeletal frameworks, low mounds and open meadows that trap and bind sediment and contribute large amounts of carbonate material to the sea floor. The character of the sea floor varies with depth and distance from shore. In very shallow inner shelf settings, wave action and storms are strong enough to winnow away fine mud, leaving well-sorted carbonate sand and gravel that migrate as ripples, dunes, and sheets. These high-energy zones may support oolitic sands where concentric layers of calcium carbonate coat small nuclei as they roll in agitated water, although the relative abundance of such deposits differs between basins. Slightly deeper on the middle shelf, water motion is still sufficient to keep the bottom well oxygenated and to supply food particles to suspension feeders, but energy levels are lower so that both skeletal fragments and carbonate mud can settle together. Here the sediment consists of a mixture of crinoid ossicles, broken shells and lime mud forming later limestones with textures that reflect moderate energy conditions. On the outer shelf below the fair weather wave base, but still within reach of storm waves, finer grained sediments accumulate and the community of organisms shifts toward forms able to tolerate lower light and less frequent strong currents. In many tropical regions, early Carboniferous reef-like structures develop where conditions allow local accumulation of rigid skeletal frameworks. These build-ups are not identical to later coral-dominated reefs, but often involve combinations of corals, bryozoans, microbial mats, and other encrusting organisms that bind sediment and construct low-relief mounds. Around these mounds, crinoid meadows and brachiopod beds extend over the surrounding seafloor, and channels and depressions host somewhat finer-grained sediment with a different assemblage of invertebrates. The resulting depositional system is a mosaic of carbonate-producing environments that grade laterally into one another over distances of kilometers. At the same time, the shelves are not isolated from the influence of land. Along some margins, especially near actively rising mountain belts, rivers deliver pulses of siliciclastic sediment to the coast. During times of high discharge and lowered sea level, sand and mud can advance onto the outer parts of the shelf, temporarily increasing turbidity and reducing light penetration. In intervening times of higher sea level and reduced clastic input, carbonate production dominates again and blankets older mixed deposits. These alternations produce mixed siliciclastic carbonate successions in some early Carboniferous basins, where layers rich in skeletal debris and lime mud alternate with beds containing more quartz sand and clay. Superimposed on these regional patterns are the sea level changes driven by the waxing and waning of ice sheets on Gondwana. Even in the early Carboniferous glaciostatic fluctuations on timescales of tens to hundreds of thousands of years cause repeated shifts in shoreline position and water depth over the shelves. When global sea level rises, epicontinental seas expand, shorelines migrate landward, and previously exposed coastal plains flood, creating new accommodation space for shallow marine sediments. When sea level falls, the opposite occurs, and large areas of the inner shelf and coastal plain emerge, subject to subaerial exposure, soil formation, and erosion. In the stratigraphic record of the shelves, these changes appear as stacking patterns of shallow marine limestones and associated facies separated by surfaces that mark pauses in deposition or brief exposure. Locally hard grounds, karst features, or thin paleosols may form at such boundaries, though their development depends on climate and the duration of low stands. On timescales shorter than the glaciostatic cycles, storms and tropical cyclones rework sediment on the shelves and influence short-term ecological patterns. Storm waves generate tempestites, which are beds formed by storm-induced currents that transport skeletal debris from shallower to deeper parts of the shelf. These beds are characterized by graded structures, erosional bases, and concentrations of broken fossils. Between major storms, background sedimentation resumes, dominated by the slow rain of biogenic particles and the continuous skeletal production by benthic communities. The combination of long-term tectonic subsidence, glaciostatic sea level changes, and high carbonate productivity allows the early Carboniferous tropical shelves to accumulate thick packages of shallow marine sediment that can reach several hundred meters in total thickness over millions of years. Within these packages, vertical changes in fossil assemblages and sediment textures record shifts in water depth energy and proximity to shore, as the position of the shoreline moves back and forth across the shelves during this part of the Carboniferous. In the early Carboniferous tropics, large drainage networks link upland source areas with lowland plains and adjacent shallow seas. Rainfall over equatorial parts of Laurussia and the northern margins of Gondwana is frequent and often intense. So many slopes and plateaus in nearby highlands supply continuous runoff to headwater streams. These streams merge into trunk rivers that cross broad lowlands lying only a small distance above sea level. The main channels occupy belts that may be tens of kilometers wide, containing active channels, abandoned loops, levees, splays, and floodplain depressions. Where relief is relatively low and discharge is high and sustained, many of these trunk systems have meandering planforms with single dominant channels that migrate laterally over time, eroding their outer banks and depositing point bars on the inner banks. In areas with higher sediment load or steeper gradients, especially nearer to uplifted source regions, channels can be more braided with multiple active threads, separated by bars of sand and gravel that shift position during floods. The style of a particular river reach depends on slope discharge variability, grain size, and the degree of bank stabilization by vegetation, which is already significant in this period due to well-rooted plant communities along many banks and floodplains. The floodplains of these rivers are extensive and nearly flat over large distances with only gentle slopes toward the sea. They are constructed from repeated deposition of silt, clay, and fine sand during overbank floods. When heavy rain in the catchment produces discharge above bankful stage, water spills over levees, and lower parts of channel margins spreads onto the floodplain and deposits a thin layer of suspended sediment as flow decelerates. Repetition of these events over tens of thousands to millions of years builds up meter-scale accumulations of fine-grained overbank deposits. Closer to the channels, natural levees form low ridges of sandier material that stand slightly higher than more distal floodplain surfaces. Beyond the levees lie lower-lying areas where water can pond for days to months after floods, forming floodplain lakes and swamps with standing or slow-moving water. Within the floodplain, abandoned meander loops become oxbow lakes soon after cut-off. These lakes fill gradually with fine sediment and organic matter, and some evolve into peat-accumulating wetlands, where plant material is preserved under reducing conditions. In the early Carboniferous, thick and laterally extensive peat accumulations are not yet as common as in later parts of the period, but local peat formation still occurs in suitable low-lying sites. The structure of the floodplain is therefore a mosaic of active channels, levee ridges, crevasse splays, lakes and wetlands that shift position over geological time as rivers avulse and adjust to changes in base level. Downstream, as these rivers approach coastal zones, gradients decrease, and channels begin to divide into distributary systems that feed deltas built out into shallow, epicontinental seas. In proximal reaches of the delta plain river, dominated segments may carry most of their sediment load directly to the shoreline, forming lobes that prograde into standing water. Mouth bars and distributary mouth deposits construct sandy bodies at or just beyond the shoreline, while finer material is carried farther offshore in plumes. The tops of these delta lobes lie near sea level and are cross-cut by distributary channels that avulse over time, abandoning older pathways and creating new ones. This process spreads sand and silt across the delta plain, producing stacked channel sand bodies encased in finer-grained floodplain and bayfill deposits. In more distal parts of the lowlands and in settings where tidal range or wave energy is higher, the interaction between river flow tides and waves modifies the channel pattern and sediment distribution. tidal currents can rework mouthbar deposits, form tidal sandbars and mudflats in estuarine embayments, and produce bidirectional current structures in channel fills. Wave action along open coastlines redistributes sand along shorebills, beach ridges, and generates shore-faced deposits that grade seaward into offshore muds and skeletal sands from nearby marine communities. In many early Carboniferous tropical basins, repeated fluctuations in global sea level, related to the waxing and waning of Gondwanan ice sheets, superimpose longer-term shifts on this lowland system. When sea level falls, base level for the rivers also falls, and trunk channels incise into their floodplains reoccupy older positions or cut new valleys. Incised valleys can concentrate fluvial deposits into narrower belts, with thicker channel sand bodies and associated coarse material. When sea level rises again, these valleys flood, creating estuarine conditions and new accommodation space for deltaic and coastal plain deposits. Over time, a complex vertical succession of fluvial channel fills, floodplain mudstones, paleosols, estuarine sands, and shallow marine sediments accumulates as the shoreline migrates back and forth across the lowland. Local climate variations within the overall humid tropical setting also influence river behavior. Periods with more evenly distributed rainfall favor perennial rivers with stable base flow, while intervals with stronger seasonality can produce larger contrasts between low stage and flood stage discharge. During drier months, channels may contract toward their thalwegs, exposing bars and lower banks to subaerial conditions and soil-forming processes. During wetter months, high discharge events rework these surfaces, erode parts of older deposits, and lay down new bar and overbank sediments. Vegetation on the floodplain responds to this hydrologic regime. Rooted plants stabilize parts of the banks and levees, increasing bank strength and encouraging meandering in some areas, while in other areas frequent reworking and high sediment loads maintain broader, more braided belts with limited vegetative cover on bars. The coevolution of rivers and vegetation in these tropical lowlands leads to floodplain deposits that include not only physical sedimentary structures such as cross-bedding and ripple lamination, but also abundant root traces, plant fragments, and incipient paleosols that record phases of relative stability between major floods. Within individual channels, bedforms and bar deposits reflect the range of flows experienced by the system. At lower flows, fine sand and silt move as ripples and small dunes across the bed, while higher flows during floods generate larger dunes and plain bed conditions with upper stage plain bed lamination. As floods wane, suspended load-dominated transport gives way to bed load-dominated movement and then to deposition. Coarser grains settle first on bar tops and channel floors, followed by finer grains that drape these structures. In some reaches, woody debris and plant stems accumulate in channel margins, or are trapped against bars, influencing local flow patterns and sediment deposition. These processes operate repeatedly during the early Carboniferous, so that over the available time interval, river systems construct lowland plains composed of stacked channel and floodplain deposits that keep pace with subsidence and slow changes in regional base level. During lower stages of flow, relatively clear water moves through confined low-stage channels within the broader belts, and fine suspended sediment gradually settles across abandoned bars and the lower parts of the floodplain, adding thin increments of silt and clay to the accumulating record of these equatorial lowlands. In equatorial regions during the early part of the Carboniferous, some low-lying basins that previously host only fluvial and shallow marine environments begin to support extensive peat-forming swamp forests. These basins lie along the tropical belt of Laurussia and the northern margins of Gondwana, where subsidence is gentle but persistent, and where the land surface remains close to sea level over long intervals. Some of the basins are foreland depressions flexed down in front of rising mountain belts. Others are intracratonic sags within older continental interiors, and still others occupy segments of former continental shelves that become emergent as sea level falls. In plan view, they form broad, shallow depressions with very low regional gradients drained by sluggish rivers and bordered by slightly higher ground that rarely exceeds a few tens of meters above base level. High rainfall associated with the equatorial circulation maintains a water table that is close to or at the surface in much of these depressions for most of the year. Under such conditions, soils in the basin interiors are saturated pore spaces. In the uppermost sediment remain filled with water and oxygen diffusion. Into the substrate is limited. This combination produces an environment in which plant productivity can be high, but decomposition is strongly inhibited, a necessary condition for long-term peat accumulation. The first extensive swamp forests in these settings develop as land plants with tree-like forms become established across large areas of the waterlogged lowlands. Dominant among them are arborescent lycopsids, relatives of modern club mosses that achieve tree stature. Their trunks are tall and relatively slender, with diameters of 1 to 2 meters at the base, in some individuals and heights of more than 20 meters in mature examples, and their crowns are restricted mainly to the upper part of the stem, where branches and leaves cluster near reproductive structures. The outer tissues of the stems consist largely of bark, with a pattern of leaf scars that form characteristic vertical or spiraling rows, while the central woody cylinder is relatively small. This anatomy reflects a growth strategy in which rapid vertical extension and early maturity are favoured over the production of massive woody trunks. These trees anchor themselves in the saturated substrate by means of specialised rooting systems known as stigmarian rhizomorphs. A stigmarian system extends laterally from the base of the trunk as a set of large horizontal axes, each bearing numerous smaller rootlets that radiate outward into the surrounding sediment. The main axes can reach diameters of several tens of centimeters, and the attached rootlets form dense three-dimensional networks in the upper decimeters of the substrate. This architecture distributes the weight of the tree over a broad area and stabilizes the plant on soft waterlogged ground that would not support a deep, narrow taproot. It also interacts with sediment dynamics, binding fine material, creating microtopography at the scale of root mounds and hollows, and influencing the movement of water in the shallow subsurface. In cross-section through a swamp forest floor, the uppermost layers consist of accumulating plant detritus, including leaves, small branches, spore-bearing structures, and fragmented bark mixed with fine sediment delivered during occasional floods. Beneath this litter layer lies peat, a compact mass of partially decayed plant tissue. Within the peat, recognizable elements such as leucopsid bark fragments, rootlets and spores are preserved, but cell walls and delicate tissues show varying degrees of decomposition depending on depth, local redox conditions and microbial activity. The lower boundary of the peat coincides roughly with the long-term position of the water table and with zones where mineral sediment content increases. Below this, more typical floodplain mudstones and siltstones appear, often containing rooted horizons where earlier generations of trees once grew. Over time, repeated colonization, growth and burial of these forests produce stacked successions of rooted surfaces, peat layers, and fine-grained clastic units. The hydrology of the early Carboniferous swamp basins is controlled by a combination of regional groundwater flow, direct rainfall, and river input. In many cases, peat-forming mires are groundwater-fed wetlands in which a constant influx of mineral-rich water from the basin margins maintains high water levels even when short-term climatic variations occur. In other sites, rainfall and surface runoff play a larger role, and the chemistry of the mire water reflects lower concentrations of dissolved ions. In both types, however, the key common factor is that water depth and water table position change only slowly relative to the growth rate of the vegetation, so that plant communities can persist long enough at particular topographic levels to build substantial peat thicknesses. Local micro-relief within the mire exerts a strong control on plant distribution. Slightly elevated areas only decimeters higher than the surrounding surface can host tree stands, where the rooting zone remains saturated but is not permanently inundated, while shallow depressions hold standing water and support more aquatic or emergent vegetation. As peat accumulates, these differences can be amplified, with some zones evolving into low ridges dominated by particular lycopsid taxa, and others remaining as pools surrounded by root hummocks and fallen stems. The forest canopy influences internal microclimate by reducing wind speeds at the surface, moderating temperature extremes, and controlling the amount of light that reaches lower levels. Under the crowns of lycopsid trees and associated plants, such as sphenopsids, ferns and seed ferns, light levels are low and spatially variable, favouring a ground layer of shade-tolerant herbs and juvenile plants. Dead stems that fall into the swamp create coarse woody debris on the surface and in shallow water, providing sites for colonisation by new plants and invertebrates, and further complicating the three-dimensional structure of the mire. Sediment supply from outside the mire is intermittent. Major river channels entering the basin tend to occupy marginal positions where their levees and splays bound or locally dissect the swamp. During exceptional floods, crevasse splays breach levees and carry sand and silt into peat-forming areas, building lobate bodies of coarser sediment over parts of the mire surface. These events can locally kill standing trees by burying their lower trunks and root systems, but in other cases the vegetation adapts by producing new roots and stabilizing the fresh deposits. Between such episodes, background clastic input is low, and most of the material added to the mire surface is plant-derived. This alternation between periods dominated by organic accumulation and events of increased clastic influx produces laterally variable sequences in which relatively pure peat benches grade into mixed organic mineral intervals, and then back to more organic rich layers. At the scale of the basin, the distribution of swamp forests is patchy rather than uniform. Areas where subsidence water supply and sediment input create a stable balance support long-lived mires with thick peat, while other areas experience more frequent channel avulsion exposure or marine incursions and carry only thin or discontinuous peat layers. Some parts of the basin interior are occupied by lakes or open water bodies with floating or emergent vegetation at their margins and with different patterns of organic accumulation. Along slightly better drained margins and on low interfluves, forest types shift toward communities dominated by seed ferns and early gymnospermous plants that tolerate more variable water tables and occasionally drier soils. In this way, a gradient in vegetation structure and composition extends from permanently wet mire centres through seasonally wet fringes to more stable, better drained upland patches, all within the broader equatorial lowland. In the atmosphere above these swamp forests, the exchange of gases reflects the high productivity and large area of the mires. During daylight, extensive photosynthesis in the canopy removes carbon dioxide from the air and releases oxygen, while at and below the surface, microbial decomposition of buried organic matter consumes oxygen and returns carbon dioxide and methane to pore waters in the atmosphere. When peat is buried deeply enough to be isolated from oxygenated groundwater, its carbon is effectively removed from short-term biogeochemical cycles. Over millions of years, the cumulative effect of such burial in equatorial basins contributes to the long-term drawdown of atmospheric carbon dioxide and to the rise of oxygen that characterizes the broader Carboniferous interval, while at the local scale the functioning of each swamp forest depends on the balance between plant growth, decay, water table position, and periodic disturbances by flooding and fire. By the Middle Carboniferous, the pattern of continents and oceans has changed from that of the earlier interval, as the converging margins of Gondwana and Laurussia approach full contact and the Rheic Ocean between them narrows. Laurussia lies at low to mid-northern latitudes and carries broad equatorial regions that host extensive lowlands and shallow seas, while Gondwana extends from low southern latitudes into polar regions and still bears large ice sheets on its high latitude sectors. The relative motion between these two large landmasses is convergent across a broad zone, and along this zone the crust is thickened, deformed and uplifted to form long mountain belts that run generally east to west across what is now the central part of the developing supercontinent. These belts, which later studies group under names such as the Variscan Alleghanian and Ouachita orogenes, are composed of stacked thrust sheets, folded sedimentary successions, metamorphic rocks and intrusions that together mark the suture where the Rheic Ocean once lay. In the regions equivalent to present North America, Western and Central Europe, and parts of northwestern Africa and northern South America, these orogenic systems form a nearly continuous chain that can be traced for many thousands of kilometers. The central sectors of the belts contain high-grade metamorphic cores and large plutonic bodies emplaced at depth during the peak of deformation, while the flanks are characterized by thick wedges of deformed sedimentary rocks that were once deposited on the continental margins and in the floor of the closing ocean. The topographic expression of these belts in the Middle Carboniferous consists of elevated ranges and broad uplands, with local relief of many hundreds to a few thousands of meters between ridge tops and adjacent lowlands, although precise heights are not well constrained. Along their length, segments differ in width and structure depending on the geometry of convergence and the presence of earlier basins or terrains. Some parts involve direct collision between continental crust from Gondwana and Laurussia, whereas others record the accretion of smaller continental blocks and island arcs that precede final suturing. To the north of the collision zone, Laurussia is affected not only along its southern margin, but also in regions where additional terrains arrive along other oceanic sutures, including zones that will later correspond to the Uralian belt between Laurussia and Siberia. To the south, the interior of Gondwana continues to support large ice sheets on its polar plateau, and outlet glaciers deliver sediment to surrounding basins. The progressive docking of the two megacontinents changes the configuration of nearby ocean basins. As the Rheic Ocean closes, its former floor is consumed in subduction zones and seaways that once separated the continents narrow to embayments and restricted arms. At the same time, the Panthalassic Ocean still occupies much of the opposite side of the globe, lapping against the western margins of the combined landmass, while the Paleotethys remains to the east, bordered by terrains that will later form parts of Asia. The closure of the Rheic Ocean and the uplift of the central Pangaean Mountains modify atmospheric circulation and patterns of precipitation by introducing an extensive high-standing barrier in the tropics and subtropics. Moist air masses drawn from the Paleotethys and the Panthalassic Ocean rise as they encounter the upstanding ranges and release their moisture as rain and snow on the windward flanks. On these sides, dense river networks carve valleys into the uplifting crust transport sediment toward adjacent fallen basins and contribute to high rates of erosion. On the leeward sides, descending air can be drier, favouring more seasonal and locally arid conditions in continental interiors that lie in the rain shadow of the mountains. In equatorial sectors where the mountains cross low latitudes, some of the foreland basins are located within the humid belt and receive both high rainfall and sediments from the ranges. These basins subside under the load of the growing origin and flexure of the lithosphere, creating space for thick accumulations of fluvial, deltic and coastal deposits close to sea level. In mid-latitude sectors, other basins experience a more pronounced seasonality in precipitation and temperature because of their position relative to the westerly winds and storm tracks that are guided by the orography. The mechanical and thermal processes operating within the orogenic belts include crustal, thickening through stacking of thrust sheets, intrusion of magmas generated by partial melting of the lower crust, and subducted lithosphere and exhumation of deeper levels, as erosion removes material from the surface. As rocks are buried to greater depths, they undergo metamorphism, changing mineral assemblages and fabric orientations in response to increased pressure and temperature. Later, as erosion strips away overlying layers, some of these metamorphic rocks and deep intrusions are brought back toward the surface, contributing to the heterogeneous composition of the highlands. The timescales involved are long compared with surface processes, so that at any given moment in the middle, Carboniferous individual segments of the belts are at different stages of uplift and exhumation. Along strike, the intensity of deformation and metamorphism varies, reflecting original variations in crustal thickness, thermal structure and convergence direction. In front of the mountain ranges, flexural subsidence forms elongated fallen basins that parallel the orogenic fronts. These basins are typically several tens to hundreds of kilometers wide and can stretch for many hundreds of kilometers along the belt. They receive thick wedges of sediment delivered by rivers draining the highlands, including conglomerates close to the fronts, sandstones farther out on the basin floor, and finer-grained mudstones and siltstones in more distal settings or in accompanying shallow marine embayments. The interplay between tectonic subsidence sediment supply and global sea level changes governs whether particular segments of these basins are occupied by non-marine environments, estuaries or shallow seas at any given time. In some equatorial regions, the foreland basins remain near sea level and host lowland systems with rivers, floodplains and coastal wetlands, while in others marine conditions persist for longer intervals. Elsewhere on the continents away from the main collision zone, intracratonic areas experience more subdued tectonic activity, but are still influenced indirectly by the reorganization of stresses associated with the assembly of the supercontinent. Some of these interior regions develop gentle sag basins that collect relatively undeformed sedimentary successions, while others remain tectonically stable and form broad uplands or plateaus where erosion dominates over deposition. On the northern side of La Russia, margins facing the Panthalassic and other oceanic domains continue to record subduction arc magmatism and episodic accretion of offshore terrains, although these processes are more remote from the central collision between Gondwana and Laurussia. At global scale, the progressive assembly of the land masses into a single contiguous entity reduces the area of shallow continental seas that once existed between dispersed continents, and increases the extent of interior continental climates far from moderating oceanic influences. However, in the middle, Carboniferous stage considered here, the amalgamation is still incomplete in some sectors, and significant segments of the margins still face open ocean basins. The mountain belts and their associated basins are not static features. As new thrusts propagate toward the forelands, and as erosion removes rock from the uplands, the locus of maximum elevation can migrate, and the shapes of the ranges and basins evolve. Sediment eroded from the highlands not only fills nearby basins, but also reaches more distant areas via extended river systems delivering sand mud and dissolved material to coastal plains and marginal seas. In this way, the Middle Carboniferous continents present a pattern in which long orogenic chains mark the sutures between previously separate plates and surrounding landscapes, respond through subsidence, uplift, erosion, and sedimentation that together shape the evolving surface of the growing supercontinent. In the middle, Carboniferous equatorial lowlands on the assembled parts of the northern continents contain some of the largest peat-forming basins of the entire period. These basins occupy a belt that follows the humid tropics, lying close to sea level and parallel to the long mountain ranges raised where major plates converge. Some basins lie immediately in front of these ranges as flexural depressions, others occupy intermontane positions between uplifts, and others form broad interior sags on older continental crust. Their shared feature is persistent subsidence at rates that keep pace with or slightly exceed the combined input of sediment and peat, so that accommodation for new deposits is continually created while the land surface remains within a narrow elevation band relative to sea level. Over distances of hundreds of kilometers along strike, these basins are segmented into subbasins by subtle structural highs and by buried paleo-highs of older rocks. But at the scale of individual peat fields, the relief is very low, commonly only a few meters between the highest natural levees and the lowest depressions. Across these nearly level surfaces, groundwater stands close to the surface, for most of the year fed by high rainfall, slow regional runoff, and in some cases by lateral flow from adjacent uplands. The climate in this belt remains persistently wet and warm, with frequent rain events and high humidity that limit evaporation from waterlogged soils. Under these conditions, swamp forests centered on arborescent leucopsids and associated plants expand to occupy large parts of the basin interiors and coalesce into regionally extensive wetland complexes. Within each basin, the distribution of environments reflect a balance between subsident sediment supply and water supply. Where clastic sediment influx from nearby uplands is low, and subsidence is moderate, peat-forming mires occupy broad tracts, interrupted only by narrow belts of active river channels. Where sediment influx is higher, belts of sand-rich fluvial deposits and associated overbank muds occupy a larger share of the basin floor and divide the mires into separate compartments. The channels themselves are often confined within belts several kilometers wide that contain active threads, older partially filled courses and crevasse splays built during exceptional floods. On either side of these belts, mire surfaces extend as flat to very gently domed laterally continuous tracts of peat that thicken toward their centers and thin toward margins where groundwater exchanges more freely with adjacent floodplains and lakes. In some sectors especially where subsidence proceeds rapidly and sea level stands relatively high, marginal parts of the basins communicate with shallow marine embayments. Their coastal peatlands occupy back barrier settings behind low barrier islands and shore-face sands, while slightly deeper waters host brackish or marine-influenced muds and sands with marine fossils. Landward from these coastal zones, the influence of tides and waves diminishes, and the peat mires are predominantly freshwater receiving only dilute dissolved ions from regional groundwater and from atmospheric inputs. Through Middle Carboniferous time, repeated changes in global ice volume on the southern supercontinent drive sea level fluctuations that affect base level in these basins. When ice sheets grow and global sea level falls, shorelines move basinward. Some marginal marine areas become exposed, and rivers incise slightly into their floodplains, locally lowering water tables near their courses. When ice sheets shrink and sea level rises again, coastal embayments advance, landward valleys flood to form estuaries, and water tables rise across the lowlands. Within the central parts of the basins where relief is minimal and hydraulic gradients are low, the Maya surfaces adjust to these changes mainly through small shifts in flooding frequency and water depth, rather than by large-scale erosion. Over many such cycles, the interaction of glaciostatic sea level change with ongoing subsidence and sediment routing produces vertical successions of strata in which coal seat earths, mudstones, sandstones, and occasional marine or brackish units stack in repetitive patterns. In upward view through one of these successions, a typical middle Carboniferous cycle begins with an erosional surface at the base of a channel sandstone, overlain by finer overbank deposits, rooted horizons that record soil formation on a stable land surface, and a coal seam representing peat, accumulated in a mire topped by more fine-grained floodplain or shallow water sediments. The thickness and continuity of individual coal seams vary, depending on how long a mire persists at a given level before being drowned, buried by clastic influx, or dissected by new channels. Some seams reach thicknesses of several meters and extend laterally for tens to hundreds of kilometers, whereas others are thinner and more local. Lateral variations follow changes in the position of channels and in the stability of the water table. In areas close to active channel belts, frequent flooding and crevasse splay deposition can limit peat accumulation to thin discontinuous layers or prevent it altogether. Farther from active channels where clastic input is low and water tables remain high, thick peats develop with high organic purity and only minor mineral admixture. The internal composition of the coals derived from these peats reflects the dominance of particular plant groups in the swamp forests, especially the bark-rich tissues and root systems of leucopsid trees, with additional contributions from sphenopsids, ferns, and seed ferns. Differences in the relative abundance of these components between seams and between parts of the same seam encode shifts in plant community composition linked to slight changes in hydrology, nutrient status, and disturbance history. Within the basins, some mires evolve toward raised bog conditions in which the surface of the peat mass lies above the level of direct groundwater influence and is sustained mainly by rainfall. In such mires, nutrient supply is more restricted, and plant communities adjust accordingly, favouring taxa that can tolerate lower nutrient availability and more acidic conditions. Other mires remain more directly connected to groundwater and to mineral-rich inflows from basin margins, and thus maintain different plant assemblages. At the scale of tens of kilometres, these differences divide basin interiors into a patchwork of peatland types, with contrasting internal structure and coal-forming potential. The time required for a single thick peat body to accumulate under these conditions can be on the order of hundreds of thousands of years, depending on net organic accumulation rate and the frequency of disruptive events. During this time, the underlying crust continues to subside and small adjustments in relative sea level continue to occur, but as long as the rate of vertical peat growth can match or exceed the rate of accommodation creation, the mire surface remains near the level of the water table and near base level. Only when conditions change sufficiently through a shift in subsidence rate, sediment influx climate or sea level, does the peat body pass fully into the geological record as it is buried beneath younger sediments, and begins the slow transition from waterlogged plant tissue to compacted coal. In a mature middle Carboniferous swamp forest within an equatorial peat basin, the view at landscape scale is of a continuous belt of forests stretching over many kilometres. But at the scale of a single stand, the structure resolves into discrete layers and repeating elements organised around the properties of waterlogged peat. The uppermost layer is formed by the crowns of arborescent leucopsids, whose trunks rise vertically from the peat surface to heights of several tens of meters before branching near the top. The stems are mostly unbranched for much of their length and carry leaf scars arranged in ordered rows, giving the outer bark a regular pattern that is visible where lichens, epiphytes, and surface films do not obscure it. Individual trees stand at distances of only a few body widths from one another in many parts of the stand, so their crowns overlap and form a nearly continuous canopy, with only small gaps where younger cohorts have not yet reached full height, or where older individuals have fallen. Within this canopy, leaves are concentrated at the distal parts of the branches, and in some taxa are borne in dense spirals or whorls, producing a layer with high leaf area relative to ground surface. Below the main Lycopsid canopy, a secondary layer includes tree ferns, seed ferns, and smaller Lycopsids that occupy spaces where light levels are reduced but still sufficient for growth. Coal-ball floras and in situ forest reconstructions indicate that these groups co-occur with the larger trees, and that they tend to form clusters or patches reflecting local microtopography and water table position. Closer to the peat surface, phenopsids and herbaceous ferns form a low understory in some areas, especially along small drainage features or around the bases of larger trunks where organic litter accumulates and water depth fluctuates over small ranges. Light conditions under the closed canopy differ markedly from those at the top. At canopy height, irradiance is strong and varies through the day according to solar position and cloud cover, while within a few meters of the ground light intensity is much lower and is dominated by diffuse radiation passing through gaps between leaves and branches. Direct beams reach the forest floor only where small gaps open, due to the fall of individual trees or branches or along narrow corridors aligned with minor channels. The lower light regime restricts photosynthesis in many potential colonists, and favours those plant groups adapted to shade, including some ferns and juvenile stages of canopy trees. The resulting vertical gradient in light contributes to the stratification of species and growth forms observed in coal swamp plant assemblages. Measurements on modern forested wetlands and modelling of vegetation structure provide constraints on likely humidity and temperature profiles in such a stand. High transpiration rates from the canopy, combined with constant evaporation from saturated peat and standing water, maintain air humidity near saturation within the understory, while limited air movement in the densely vegetated interior reduces convective heat exchange. These conditions suppress daily temperature amplitude near the ground, compared with open settings, so that the peat surface experiences relatively small diurnal fluctuations. Near the canopy top, in contrast, air masses interact more directly with regional winds and exhibit larger short-term variability in temperature and vapor content. Within the peat and near-surface sediment, water content remains high throughout the year. The uppermost decimeters consist of a fibrous zone, where plant litter, root mats, and fine sediment intermingle, grading downward into more compact, partially decomposed peat. Redox conditions in these layers are generally reducing, especially below the depth to which oxygenated surface water can penetrate. Geochemical and sedimentological studies of analogous wetland soils show that where water tables remain high and residence times are long low, redox potentials limit aerobic decay and favour the preservation of organic structures, while also influencing the solubility and mobility of elements such as iron and manganese. In the Carboniferous swamp forest, similar processes act within a substrate dominated by plant material rather than mineral grains. The rooting systems of the canopy trees occupy a large volume of this near-surface zone. Stigmarian rhizomorphs extend laterally from the base of each Lycopsid trunk, with large horizontal axes penetrating the peat and bearing numerous smaller rootlets that radiate outward and downward. Fossil evidence shows that these rootlets form dense, highly branched networks that permeate the substrate and create a fine-scale, three-dimensional framework. Around each trunk, the concentration of roots produces low mounds or hummocks that stand slightly above the surrounding peat surface, often by only a few tens of centimeters. Between these hummocks lie shallow hollows that hold standing water for long periods after rainfall or flooding events. The vertical difference between hummocks and hollows is small, but it is enough to produce consistent gradients in water depth, oxygen availability, and nutrient concentration. Plants that tolerate permanent inundation occupy the hollows, while those requiring only saturated but not submerged substrates concentrate on the hummocks. Tree ferns and some seed ferns are more common on the slightly elevated surfaces, whereas certain lycopsids and sphenopsids can colonize both microenvironments depending on water table behavior. At points where small distributary channels or drainage lines cross the forest floor, the vegetation becomes more open. Here, repeated scouring by slow-moving water and deposition of silt and fine sand restrict the establishment of deep-rooted trees and favour stands of more disturbance-tolerant plants. Rooted evidence and sedimentary structures preserved in channel margin deposits from Carboniferous basins indicate that these linear features act as conduits for both water and fine sediment into and out of the mire interior, and that their margins carry distinctive assemblages compared with the peat plateau surfaces. Within the canopy and understory plant reproduction occurs continuously on Carboniferous timescales. Many lycopsids are heterosporous and bear their reproductive structures in terminal cones or strobili at the tops of their stems or branches. When these structures mature, they release large numbers of spores into the air column above the forest. Some spores settle within short distances of the parent plant, becoming incorporated into the peat near the base of the trunk, while others travel farther before deposition. Spore assemblages preserved in coal and associated sediments provide records of the plant communities contributing material to the mire and show that lycopsids dominate the spore rain in many middle Carboniferous coals, with additional contributions from ferns, sphenopsids, and seed ferns. On the forest floor, fallen leaves, bark fragments, roots, and entire trunks accumulate in varying states of decay. Some stems fall while still bearing attached reproductive structures, adding cones and associated spores directly to the litter layer. Others topple after decay has weakened the base or after disturbance by localized flooding or minor slumps in the peat mass. These fallen logs create obstacles that divert shallow surface flow trap, suspended particulate matter, and provide elevated microsites that may remain slightly less saturated than the surrounding peat. Over time, they too are incorporated into the peat body as their tissues break down and are compressed by overlying material. The microhabitats created by this structural complexity influence not only plant distribution, but also the activity of invertebrates and microorganisms that process organic matter. Although the taxonomic composition of these coal swamp forests differs strongly from that of modern tropical rainforests, studies of species richness in late Carboniferous wetlands indicate that local diversity at the scale of individual stands stabilizes at values that reflect an ecologically saturated but compositionally distinct community, with relatively few dominant taxa and many less abundant associates. The mature middle Carboniferous swamp forest canopy is therefore a vertically and laterally structured system in which light, water and substrate conditions vary over short distances, and where the dominance of arborescent lycopsids supported by extensive stigmarian root networks in waterlogged peat defines much of the physical environment experienced by the understory plants and the organisms that use the forest floor and peat surface. Within a middle Carboniferous swamp forest basin, the animal community associated with the peat mires and their margins includes a range of arthropods and early tetrapods that occupy different positions in the structurally complex wetland. The physical template is the leucopsid-dominated forest, and its hummock and hollow micro-relief, the shallow pools and linear drainage features at the surface of the peat, and the nearby belts of rivers and crevasse splays that bring in mineral sediment. Above, between and within these elements, terrestrial arthropods move across the forest floor and through the understory, while amphibious and aquatic vertebrates inhabit standing and flowing water and make excursions onto land. The arthropod assemblage contains both small forms and very large taxa that reach body sizes not seen in most later environments. Fossils and trackways from coal-bearing and fluvial successions indicate the presence of Arthropleura, a myriapod related to millipedes, which in some specimens exceeds 1 metre and possibly approaches lengths of more than 2 metres, making it the largest known land arthropod. Its articulated exoskeleton consists of numerous broad-jointed segments arranged in a series that covers the dorsal surface and flanks. Each segment carries a pair of lateral plates that meet along the midline. When such an animal moves across the peat surface or over firm substrates near channels, multiple pairs of legs contact the ground in coordinated waves, distributing its weight across many points and allowing locomotion over soft ground and shallow water films. Trackways attributed to Arthropleura in fluvial sandstones and overbank deposits show parallel rows of imprints and a central body drag or impression, in some cases indicating that individuals traverse floodplains, levees, and sparsely wooded areas, as well as zones near coal-forming wetlands. The diet of Arthropleura remains a topic of discussion, with early interpretations favouring herbivory on litter or detritus, and later suggestions including omnivory or occasional predation, but in either case its presence represents a large consumer of organic matter in these systems. Other terrestrial arthropods in the swamp forests include pterygote insects and their relatives, some of which reach large sizes by later Paleozoic standards. Dragonfly-like griffinflies such as Meganeura, known from late Carboniferous and Permian deposits, attain wingspans of several tens of centimetres and are reconstructed as aerial predators that exploit open airspace above and between forest stands. Their fossils are more often preserved in lacustrine or marginal marine settings than in peat itself, but they represent an element of the aerial fauna associated with these landscapes. Large scorpions and other arachnids, including forms such as Pulmonoscorpius with body lengths approaching several tens of centimetres, occupy the forest floor, and margins preying on smaller arthropods and potentially on juvenile tetrapods. In the context of the Carboniferous atmosphere with oxygen levels elevated above many modern values for part of the interval, the respiratory physiology of arthropods imposes constraints and opportunities. The tracheal system of insects and other terrestrial arthropods operates by diffusion and convection of gases along internal tubes, and experimental and modelling studies indicate that higher atmospheric oxygen, partial pressure can increase the maximum attainable body size by enhancing oxygen delivery and reducing the need for disproportionately large tracheae. The geochemical record suggests that during the middle to late Carboniferous atmospheric oxygen may reach values substantially above present atmospheric levels, although estimates vary and uncertainties remain. The association between this hyperoxic interval and the occurrence of giant arthropods supports a role for oxygen in permitting such sizes while coexisting smaller arthropods, and the persistence of some large taxa into times of lower oxygen indicate that ecological factors and lineage-specific traits also influence maximum body size. In the aquatic and amphibious component of the swamp fauna, early tetrapods, many of them conventionally grouped as temnospondylls, and other basal forms inhabit a range of water bodies within and around the peatlands. Fossil assemblages from Westphalian wetland deposits in Euramerica show that amphibian-grade tetrapods are common in coal measure successions, often preserved in channel fills, floodplain ponds, and roof shales above coal seams. These animals possess robust skulls, limb girdles, and vertebrae suited to both aquatic propulsion and short-distance locomotion on land. Many retain lateral line grooves on the skull, indicating reliance on waterborne sensory cues, and their limb morphologies suggest frequent use of bottom walking and slow swimming in shallow waters rather than sustained high-speed pursuit in open water. In the swamp forest basins, such tetrapods occupy permanent pools in hollows between peat hummocks, abandoned channel segments on the floodplain, and quiet reaches of small distributaries. They prey on invertebrates and smaller vertebrates, including fish in connected water bodies, and surface-dwelling arthropods that enter the water film. Trackway evidence and body fossils together show that some amphibians use the peat surface itself during damp periods, moving between pools or exploiting prey in saturated litter. In more open alluvial settings at the margins of coal basins, large areopid temnospondyls and other forms share space with arthropleura and similar myriapods as indicated by associated trackways in fluvial sandstones outside of thick coal successions. This co-occurrence shows that the interface between dense swamp forest and more open floodplain or levee environments hosts mixed assemblages in which large arthropods and large amphibians interact. Early amniotes, represented by small reptile-like tetrapods capable of laying eggs with more resistant outer coverings, appear in some of these middle Carboniferous wetland landscapes, particularly on slightly better drained substrates adjacent to the mires. Their remains are often found in deposits that indicate proximity to water, but not permanent inundation, such as levees, crevasse splays, and drier parts of the floodplain, suggesting that they exploit niches where access to land-based food and avoidance of fully aquatic predators confer advantages. Within the swamp interior, invertebrate faunas also include numerous smaller arthropods that rarely fossilize in place, but are inferred from isolated sclerites, coprolites, and analogies with better preserved assemblages in siderite concretions and other exceptional preservation sites. These likely comprise detritivorous millipedes and other myriapods of small size classes, ground-dwelling insects feeding on litter and fungi, and predators such as smaller arachnids that occupy microhabitats on and within the peat surface among root mats and underfallen stems. Their activity contributes to fragmentation and early-stage decomposition of plant material before anoxic conditions deeper in the peat halt further break down. The composition of the animal community varies across microhabitats. On slightly elevated root hummocks that remain only seasonally inundated burrows and trackways indicate frequent passage of terrestrial arthropods and small tetrapods. In shallow hollows with standing water, the faunal assemblage shifts toward aquatic or semi-aquatic taxa, including larvae of insects, small crustaceans, where water chemistry permits, and juvenile tetrapods. Along small channels and drainage lines, the combination of firmer substrates flowing water and periodic silt deposition creates corridors where trackways are more commonly preserved, recording repeated use by larger vertebrates and large arthropods. Over intervals of thousands to tens of thousands of years, these communities respond to changes in water depth, peat accumulation, and plant community composition. But within the middle Carboniferous equatorial belt as a whole, the association of giant arthropods, diverse arthropod assemblages of more ordinary size, and a suite of amphibious and early amniote tetrapods remains a consistent feature of coal swamp and adjacent lowland ecosystems. In the middle Carboniferous equatorial belt, the landscapes surrounding the Great Peat Basins include uplands, interfluves, and broad floodplains that differ in hydrology and vegetation from the permanently saturated swamp interiors. At regional scale, the surface is a composite of low mountain flanks, gently sloping piedmonts and basin margin plains that descend toward the coal-forming depressions. Relief between the highest local uplands and the basin floors is measured in hundreds of meters, but gradients over tens of kilometers are low, so that extensive tracts of land fall into intermediate positions, where drainage is better than in the mires, yet water remains available for much of the year. On the slopes of the orogenic belts that rise where major plates converge, rainfall is high, but the combination of steeper gradients and permeable weathering mantles allows water to move downslope more rapidly than in the basins. Runoff from frequent storms incises networks of valleys that carry seasonal or perennial streams, while intervening ridges and shoulders support soils that drain between rainfall events. These upland soils develop thicker unsaturated zones and experience more frequent alternation between wet and dry states than the permanently waterlogged substrates of the peatlands. In many middle and late Carboniferous successions, such conditions are later recorded by paleosols with features such as slicken sides, wedge-shaped peds, and carbonate nodules that indicate clay shrink swell behavior and episodes of soil drying. In the time slice considered here, comparable processes act on weathered profiles along foothills and interior plateaus, generating soil landscapes where rooting depth, redox conditions, and nutrient availability vary along Catini from well-drained upper slopes to more poorly drained toe slopes and valley bottoms. The vegetation on these uplands and well-drained lowlands differs from that of the coal swamps. Leucopsid tree stands characteristic of permanently saturated mires become less common as drainage improves and as the frequency of soil saturation events declines. In their place, assemblages dominated by seed ferns, corditalian trees, and early gymnospermous plants occupy slopes and interfluves. These plants bear seeds and produce more robust woody tissues, and many are interpreted as better adapted to substrates that experience seasonal moisture deficits compared with the ever-wet peatlands. Their canopies are often less densely closed than those of lycopsid swamp forests, allowing greater light penetration to the understory, where smaller ferns, sphenopsids, and herbaceous forms occupy gaps between tree crowns. On upper parts of slopes, tree spacing increases as soil depth decreases and as exposure to wind and insulation intensifies. Roots follow fractures and weathering fronts downward, stabilizing regolith on inclines and contributing to mechanical and chemical weathering of bedrock. Leaf litter accumulates as a discontinuous layer on surfaces that may dry between rainfall events, and decomposition proceeds under fluctuating redox and moisture regimes, producing humus horizons that differ chemically from the peat horizons of the basins. Along lower slopes and on piedmont aprons, where colluvial and alluvial processes interact, vegetation transitions into belts, dominated by mixed communities in which wetland elements and more drought-tolerant plants coexist. Local differences in substrate texture and water table depth create patches where tree ferns and calamitian sphenopsids occupy wetter microsites, while seed ferns and corditalians are more frequent on slightly elevated bars or fan lobes. Seasonal streams crossing these belts build small alluvial fans and distributary networks that migrate laterally over time, leaving behind sequences of gravelly and sandy lenses interbedded with paleosols. In such settings, wetlands are often seasonal rather than permanent. During wet parts of the climatic cycle, when rains concentrate in particular months under monsoon-like circulation patterns, water accumulates in closed depressions and on low interfluves, forming shallow ponds and marshes. These features may persist for weeks to months, supporting emergent vegetation and providing habitat for aquatic and semi-aquatic organisms. During drier intervals, many of the same depressions shrink or dry out completely, leaving desiccation cracks, mud curls and oxidized surfaces that favor colonization by plants and animals tolerant of variable water supply. Soils forming under this alternation of flooding and drying develop structures such as deep cracks that open during dry phases and close when the clay-rich matrix swells again in wet phases. On broad floodplains downstream from the uplands, but still outside the main peat-forming centres, large rivers with higher seasonal discharge contrast cross surfaces that stand a few metres above long-term base level. Their channels are deeper incised into the substrate than those in the distal coal basins, and bars of sand and fine gravel become exposed for longer periods between floods. Overbank flooding still builds natural levees and deposits sheets of silt and fine sand, but the frequency of inundation at any given point on the floodplain can be lower than in the ever-wet equatorial basins, especially in sectors that lie in partial rain shadows of the central mountain belts. Paleosol profiles preserved in some of these floodplain deposits show evidence of root systems that penetrate through multiple flood layers, suggesting that plants can occupy surfaces for extended intervals without drowning. Carbonate nodules and mottled red to brown colouring indicate that oxidation dominates over reduction in much of the soil matrix for significant portions of the climatic cycle, consistent with better ventilation of the substrate and longer periods of dryness. Vegetation on these seasonally flooded plains often arranges itself along subtle gradients in height and drainage. Channel margins and levee crests carry tree stands with deeper roots and greater tolerance of temporarily lowered water tables, including some early gymnospermous taxa and robust seed ferns. More distal floodplain positions where water lingers longer after floods support mixed stands including tree ferns and other plants that require regular saturation but can withstand occasional exposure. In the lowest lying back swamps and oxbow lakes, communities resemble those of the coal basins more closely with elements of wetland flora, established in areas where standing water persists through much of the year. The faunal assemblages of these uplands and floodplains reflect their intermediate hydrologic position between permanently wet peatlands and fully terrestrial interiors. Amphibious tetrapods still depend on ponds channels and seasonally inundated depressions for breeding and larval stages, but some taxa exploit terrestrial prey on better drained ground, more frequently than do their counterparts in the deepest swamps. Early amniotes, where present, use the drier interfluves and levees as primary habitat, taking advantage of soils that support burrows or nests above the maximum flood level. Trace fossil assemblages from such settings include footprints and trackways on mudflat and overbank surfaces that record repeated passage of small to medium-sized vertebrates across substrates that dry and harden between wet phases. Invertebrate communities include ground-dwelling arthropods in litter layers under open canopies, and assemblages adapted to temporary aquatic habitats in seasonal ponds. At the interface between these better-drained terrains and the peat basins, sharp changes in substrate and vegetation over distances of only hundreds of metres create ecotones where elements of both wetland and dryland biotas overlap. Over Middle Carboniferous time, these uplands and seasonally wet lowlands persist as integral components of the tropical belt, supplying sediment and dissolved material to the basins, hosting plant and animal communities with different water and substrate tolerances from those of the Mayas, and responding sensitively to shifts in rainfall patterns and base level without losing their role as the slightly drier counterparts to the permanently saturated coal-forming wetlands nearby. In the late Carboniferous, during the later stages of the Pennsylvanian, the planet remains in an icehouse state, but the behavior of the ice sheets and the associated climate shows a pattern of repeated shifts in ice volume and hydrology rather than a single uniform interval of glaciation. Large ice masses still occupy high-latitude regions of Gondwana, particularly over parts of what are now South America, Southern Africa, Antarctica, Australia and India. But geological evidence indicates that these ice centres wax and wane in a series of discrete glacial episodes separated by relatively warmer interludes that last on the order of 1 to several million years. During colder phases, ice sheets expand across uplands and plateaus. Glacial erosion intensifies and meltwater and icebergs deliver sediment to marine basins around the Gondwanan margin. During warmer phases, some of the ice retreats, exposing previously glaciated terrain and contributing large volumes of meltwater to adjacent seas. These changes in ice volume drive global sea level fluctuations of tens to more than 100 meters, so that shallow epicontinental seas repeatedly advance over and retreat from low-lying continental interiors. In the late Carboniferous, these glaciostatic cycles remain a dominant control on the extent of shallow seas and the distribution of coastal and nearshore environments. Against this background of ice-driven sea level change, atmospheric greenhouse gas concentrations, especially carbon dioxide, remain generally low compared with many other Phanerozoic intervals reflecting long periods of carbon burial in coal and organic-rich sediments and enhanced chemical weathering of silicate rocks. High-resolution proxy records from paleosols and fossil leaves show that late Carboniferous carbon dioxide is often at or below levels that sustain extensive glaciation, while oxygen may be elevated relative to modern values for at least part of the interval, although absolute percentages and temporal trends differ between models. The combination of low carbon dioxide and large ice sheets maintains relatively cool global mean temperatures, but within this icehouse state the distribution of temperature and rainfall across latitudes and between ocean and land responds sensitively to changes in ice extent, paleogeography and orbital forcing. In the equatorial belt of Euramerica, where earlier in the Carboniferous extensive coal-forming rainforests and mires occupy broad lowlands, climate signals in the late Moscovian and Casimovian stages record a shift from persistently humid conditions toward climates that are still warm but more seasonal and in some intervals drier overall. Studies of paleosols in succession spanning these stages show a decrease in features associated with permanently waterlogged soils and an increase in indicators of better drained, more stable landscapes, including red and brown coloration development of well-expressed soil horizons and presence of carbonate nodules and vertic structures that reflect repeated drying and rewetting. At the same time, plant fossil assemblages in Euramerican basins record stepwise changes in the composition and continuity of wetland floras, with a decline in the dominance of leucopsid tree elements that require constantly saturated substrates, and an increase in taxa such as tree ferns and seed ferns that tolerate more pronounced dry periods, signaling that hydrological regimes in at least some parts of the tropics now include clearer wet and dry seasons. From the perspective of atmospheric circulation, the late Carboniferous equatorial zone remains a region of net convergence and rising air, but the contrast between oceanic and continental surfaces becomes more important as continental areas coalesce into a larger supercontinental mass. Where large land areas cluster near the equator, seasonal heating contrasts between land and adjacent seas can strengthen monsoon-like circulation with onshore winds and heavy rainfall, concentrated in certain parts of the year, and a shift toward drier offshore flow in others. With ice sheets present on Gondwana, changes in orbital parameters that alter seasonal insolation patterns at high latitudes influence the growth and decay of ice, and through sea level responses the position of shorelines and the distribution of shallow seas that supply moisture to low latitudes. Climate records from marine and continental successions in several basins show that glacial maxima marked by low stands and increased delivery of glacially derived sediment to the oceans coincide with signs of increased aridity and seasonality in some equatorial lowlands, whereas interglacial intervals with higher sea level are associated with more laterally extensive wetland deposits. In equatorial Euramerica, this pattern appears as a shift from earlier cold successions characterized by thick laterally continuous seams and frequent hydromorphic paleosols toward late Carboniferous successions, in which coal seams become thinner and less continuous. Red beds and calcareous paleosols are more common, and non-marine sediments include features indicating longer intervals of subaerial exposure and soil development. Such changes imply that while rainfall remains sufficient to sustain wetlands in refugial areas, the frequency and duration of dry intervals increase, and soil moisture regimes on many interfluves and basin margins move away from permanent saturation. The process that later literature terms the Carboniferous rainforest collapse is embedded in this climatic context. In the late Moscovian and early Casimovian equatorial coal forests in Euramerica lose their former continuity and become fragmented into separate blocks, confined mainly to areas where local topography and hydrology still permit year-round wet conditions such as subsiding basins and structurally controlled depressions. Between these refugia landscapes with more seasonal climates expand supporting vegetation that is more tolerant of dry periods and better drained substrates. The underlying climate driver is not a uniform shift to desert conditions, but an increase in the amplitude of seasonal contrasts and in the frequency of intervals when rainfall fails to keep soil saturated, especially on uplands and basin margins. Evidence from conodon oxygen isotopes and other marine proxies indicates that global cooling and glacial expansion, contemporaneous with these terrestrial changes, reduce sea surface temperatures and lower sea level, decreasing the area of shallow tropical seas that previously served as strong moisture sources and altering atmospheric moisture transport pathways. As the ice sheets grow and sea level falls, equatorial shelves and interior seaways shrink, and parts of the lowlands that had been influenced by proximity to warm water bodies become more continental in their climate, with larger seasonal temperature ranges and more susceptibility to dry spells. As sea level later rises during deglaciation episodes, some coastal wetlands and nearshore areas are re-established, but the composition of the adjacent vegetation and the degree of connectivity between forested wetlands and other habitats no longer match the earlier Carboniferous pattern. In the coal-bearing basins themselves, the late Carboniferous climatic shifts express themselves through changes in flooding frequency, water table stability, and the relative duration of phases conducive to peat accumulation. During intervals with cooler, wetter conditions, local peat-forming mires can still develop, especially in structurally low parts of basins, where subsidence helps maintain high water tables. During intervals with stronger seasonality or regional drying, these mires may contract, peat accumulation slows or ceases, and oxidation and pedogenesis affect previously waterlogged surfaces. The resulting stratigraphic record consists of more strongly cyclic successions, in which coal seams are interbedded with thicker packages of non-peat deposits, showing features of better drained floodplains and soils. Over the late Carboniferous portion of the interval, the combined effect of discrete glacial episodes on Gondwana low, but fluctuating carbon dioxide levels reorganized continental configurations, and feedbacks from extensive earlier carbon burial yields, a climate system in which equatorial regions experience a transition from persistently humid coal forest conditions toward more heterogeneous patterns of rainfall and seasonality, with directly observable consequences in the extent, continuity and internal hydrology of the coal swamps that had dominated many lowlands in earlier stages of the Carboniferous. In the late Carboniferous, the vegetation of equatorial Euramerica and neighbouring regions does not disappear, but reorganizes into a set of floras with different composition and spatial relations compared with earlier stages of the period. During the earlier middle Carboniferous wetland basins over large areas are dominated by arborescent lycopsids, with tree ferns, sphenopsids, and seed ferns present, but often subordinate in biomass within the peat-forming mires. By late Moscovian and into Casimovian, time plant macrofossil and spore records from coal-bearing and associated strata show that the dominant structure of these forests changes. In many basins, the relative abundance of lycopsid declines, while remains of tree ferns and seed ferns become more common. Assemblages that were once overwhelmingly composed of lycopsid bark and root material now include a larger proportion of fern fronds, fern stems and seed plant organs. In some successions, this shift occurs through a series of steps with local increases in opportunistic fern taxa, preceding more persistent changes in canopy structure, followed by intervals in which lycopsid taxa suffer regional extinctions or substantial range contractions. The decline of arborescent lycopsids is not synchronous everywhere. In some intramontane basins and refugial settings, lycopsid-dominated mires persist into the latest Carboniferous, and even into the early Permian, whereas in many Euramerican foreland and interior basins, their representation in coal seams drops from high percentages of the biomass in earlier Westphalian coals to much lower values by late Westphalian and Stephanian times. The pattern is influenced by local hydrology and subsidence, as well as by broader climatic changes. Where water tables can no longer remain permanently at or near the surface over large contiguous areas, conditions favour plants that can tolerate fluctuating saturation and periodic drying. Under these circumstances, tree ferns increase in importance within remaining wetlands. They possess trunks and fronds adapted to high humidity shaded environments, but can persist under somewhat more variable water regimes than many lycopsid trees, as indicated by their occurrence in paleosols that show evidence of better drainage. Seed ferns or pteridosperms also become more prominent. These plants combine fern-like fronds with ovule-based reproduction and woody stems, and are represented by multiple families that occupy a range of habitats from wetland margins to better drained floodplains. Their seeds are protected by integuments and attached to fronds in ways that permit dispersal and germination under conditions where free water for gamete transfer is intermittent rather than constant. Tree fern and seed fern dominated assemblages in late Carboniferous successions record this shift at the level of both macrofossils and dispersed spores and pollen. In wetland sequences, coal seams formed during this time often contain higher proportions of fern and seed. Fern material with lycopsid remains still present but much reduced. At the same time, plant assemblages preserved in overbank mudstones, crevasse splay deposits, and better drained floodplain paleosols frequently show a distinct composition dominated by seed plants such as medullus and pteridosperms, and corditalian trees with subordinate ferns and sphenopsids. These differences reflect a strengthening separation between wetland floras adapted to saturated substrates and dry land, or seasonally dry floras adapted to soils that experience regular exposure and varying moisture, Corditalian trees, which are gymnosperms with slender trunks, narrow leaves, and reproductive structures based on seeds and pollen, occupy important roles in these drier habitats. Fossil wood and foliage from late Pennsylvanian upland and alluvial plain settings indicate that corditalians can form substantial stands on higher, better drained parts of the landscape, including interflues and slopes above coal-forming basins. Their rooting systems penetrate deeper into mineral soils than those of many wetland taxa, and their seed-based reproduction allows recruitment in microsites that are not continuously wet. Early conifer-like trees and additional gymnosperm lineages are present in some of these assemblages, although their diversity and abundance are generally lower than those of seed ferns and corditalians at this time. As climatic seasonality increases and some areas experience longer dry intervals, these seed plant-dominated communities expand spatially, particularly on basin margins and in more continental interior regions. Paleobotanical studies show that the composition of late Carboniferous floras can be grouped into broad categories, corresponding to wetland and seasonally dry environments. Wetland floras retain a mixture of lycopsids, tree ferns, sphenopsids, and seed ferns, though with changing relative abundances, while dryland floras are dominated by seed plants, including seed ferns, corditalians, and early conifer-like taxa with fewer strictly hydrophilic forms. Within each category, local environmental variables such as substrate texture, soil chemistry, and disturbance regime generate further differentiation. For example, in intramontane basins with peat mires surrounded by alluvial fans, stands of a single lycopsid genus may dominate mire surfaces. Tree ferns may occur preferentially during later stages of mire development or on its fringes, and seed ferns may be concentrated on higher levees or fan lobes. In contrast, in wide alluvial plains where dry season water deficits become more pronounced, corditalian-dominated stands may occupy broad areas, interspersed with patches of mixed seed fern and fern vegetation in swales and along minor channels. At the level of individual plants, the shift from spore-based to seed-based reproduction in many components of the late Carboniferous vegetation has direct ecological implications. Spore-producing lycopsids, sphenopsids and ferns rely on free water for sperm motility during fertilization, which restricts successful reproduction to periods when surfaces are wet or when films of water connect gametophytes. Seed plants encapsulate the female gametophyte and embryo within a protective structure and deliver sperm via pollen, reducing the requirement for external water during the reproductive phase. This difference means that seed plants can reproduce reliably in environments where soils may dry between rainfall events, and where standing water is absent for extended periods. The expansion of seed plants in late Carboniferous dryland floras is thus consistent with the development of more strongly seasonal or locally drier climates, and with the presence of soils that undergo repeated wetting and drying cycles. Within the remaining wetlands, seed plants also play important roles. Some seed ferns and gymnosperms specialize in wetland margins and seasonally flooded flats occupying substrates that are waterlogged for part of the year, but not permanently inundated. Others occupy disturbed sites within mires, such as levee crests, crevasse splays, and abandoned distributaries. Their growth forms range from small shrubs to large trees, and their seeds can use brief windows of favorable moisture and temperature to germinate and establish before conditions change again. In late Carboniferous coal swamps, anatomically preserved material demonstrates that seed plants contribute significantly to the canopy and subcanopy, in some stands especially during intervals when lycopsid dominance is reduced. The spatial arrangement of changing forests in late Carboniferous landscapes reflects the combined influence of climate topography and basin structure. In some equatorial basins, reduced rainfall and greater seasonality shrink the area of permanently waterlogged ground, confining true mire vegetation to topographic lows and structurally controlled depressions, while adjacent high ground support seed plant dominated dryland forests and woodlands. In other basins, continued subsidence and favourable hydrology maintain larger wetland extents, but even there the internal composition of the forests shifts toward larger contributions from tree ferns and seed ferns. Between basins, differences in proximity to oceans, position relative to mountain belts, and degree of continentality produce regional variations in the timing and magnitude of these changes, so that at any given time some areas retain more of the earlier leucopsid-rich character, while others have already transitioned to seed plant-dominated assemblages on most surfaces. Over the late Carboniferous interval as a whole, the vegetation changes trace a trajectory in which the once widespread, relatively uniform equatorial coal forests of the earlier Carboniferous are replaced by a more heterogeneous set of forest and woodland types occupying different hydrological and edaphic niches, with seed plants playing an increasingly prominent role in many of the better drained and more seasonally dry parts of the landscape. In late Carboniferous lowlands and uplands around the equatorial belt, early amniotes occupy habitats that differ in important ways from the permanently saturated interiors of the coal-forming mires. The land surface is divided into zones that range from ever-wet peat swamps in structurally low positions through seasonally wet floodplains to better drained interfluves and upland slopes. The early amniotes are concentrated in the latter two categories, where soils drain between rainfall events and where substrates remain firm for longer intervals. In these settings, the combination of seed plant-dominated vegetation, more open canopies, and more stable ground favours small to medium-sized vertebrates capable of sustained terrestrial activity. The fossil record indicates that by the late Carboniferous crown group amniotes are already present, and that they include both sauropsid and synapsid lineages. Hylonomus, a small reptile known from articulated skeletons preserved within hollow leucopsid stumps at Joggins in the Canadian Maritimes, represents one of the earliest undisputed sauropsids, while Archaeopteris, from broadly similar age deposits, is among the earliest recognized synapsids. These taxa have lightly built skulls with numerous sharp teeth, limb girdles, and limb bones suited to weight-bearing on land and vertebral columns that allow more sustained locomotion on firm substrates than that of many contemporaneous amphibians. Their body sizes are modest, typically on the order of a few tens of centimetres in length, which is compatible with moving through understory vegetation and using small shelters in soils and rotten wood. The key feature that distinguishes these animals as amniotes is the structure of their reproductive system, inferred from phylogenetic position rather than directly preserved eggs. The amniote egg includes internal membranes that enclose the embryo, the yolk and waste products, and it possesses a shell or outer covering that reduces desiccation relative to the unprotected eggs of amphibians. Even if the earliest amniote eggs are small and laid in moist microhabitats such as leaf litter or rotting wood, their reduced dependence on standing water means that reproduction can occur on better drained ground and in locations farther from permanent ponds and streams. This capacity enhances the use of upland and interfluve habitats, complementing morphological traits such as more robust vertebral connections and more firmly attached limbs. In the landscapes adjacent to late Carboniferous coal basins, these animals move across levees, stable floodplain surfaces and low upland ridges that support seed plant-dominated vegetation. The plant cover in such areas includes stands of corditalian trees seed ferns and early conifer-like gymnosperms, with ground layers of ferns and sphenopsids. The canopy is generally less dense than in leucopsid swamp forests, permitting a mosaic of sunlit patches and shaded zones on the forest floor. Leaf litter accumulates in irregular layers, separated by intervals of partial decomposition and soil formation. Within this litter, and the upper few decimeters of mineral soil, invertebrate communities provide a range of potential prey items including small arthropods, annelids, and juvenile forms of larger species. The small-bodied amniotes exploit this resource base, using a combination of visual and chemical cues moving along the surface and within shallow burrows or crevices. Their skull and tooth morphology in many cases suggests a primarily insectivorous or small vertebrate diet, although omnivory is likely in some groups. The locomotor apparatus of early amniotes reflects a compromise between sprawling limb posture, inherited from earlier tetrapods, and enhanced stability on land. Limb girdles are robust and attached to the axial skeleton in ways that transmit forces effectively during walking, while limb segments bear articular surfaces that permit a range of movements, suitable for negotiated terrain with obstacles such as roots and fallen branches. Trackways preserved in late Carboniferous strata attributed to small reptile-like tetrapods show alternating patterns of fore and hind footprints, with relatively narrow gauge and distinct digit impressions, consistent with coordinated walking gaits on subaerial substrates. In areas where soils dry sufficiently between rainfall events, some amniotes excavate shallow burrows or use pre-existing cavities for shelter and reproduction, as suggested by the occurrence of articulated skeletons in tree stumps and crevices in some fossil localities. The spatial distribution of amniotes across the landscape is influenced by proximity to water vegetation structure and substrate properties. Close to the margins of peat basins where ground remains moist for much of the year, and where water bodies and channels are common, amphibians still dominate the vertebrate assemblage, and amniotes are present but less abundant. Moving upslope onto levees and interfluves with better drainage, the proportion of amniote remains in fossil assemblages increases relative to that of amphibians, suggesting that physiological tolerance to drier conditions and reproductive independence from standing water allow these animals to use habitats that amphibians occupy less effectively. On higher ground and in more interior continental regions where redbed successions with well-developed paleosols indicate greater seasonality and longer dry intervals, the vertebrate faunas in late Carboniferous rocks show an even higher representation of amniote taxa, including more derived synapsids and sauropsids. For the late Carboniferous portion of this trend, the expansion of amniotes into such settings is already underway. Within the late Carboniferous ecosystems, ecological partitioning between amniotes and amphibians is evident not only in terms of moisture regimes but also in microhabitat use and feeding ecology. Amphibians with aquatic larvae and often semi-aquatic adults remain tied to ponds, lakes, and slow-moving channels, where they feed on aquatic invertebrates and small fish, and where they reproduce in water. Amniotes, by contrast, can range more widely over land, including into areas where surface water is present only intermittently. Their eggs can be laid in hidden sites on land that retain enough humidity for embryonic development without immersion, and hatchlings emerge directly as air-breathing juveniles with limbs suited to walking. The timing of breeding and growth in amniote populations is likely linked to seasonal cycles in rainfall and temperature, with egg-laying favoured during intervals when soils are moist but not saturated, and when food resources for hatchlings are abundant on land. From the standpoint of habitat structure, early amniotes make use of multiple vertical levels in the vegetation. Most taxa inferred from skeletal proportions and trackways appear to be ground-dwelling or low-level climbers, but some may ascend low trunks and branches to access prey or shelter. Their claws and digits provide traction on rough bark and among plant debris, and the keratinous coverings of their skin reduce water loss during such excursions. On open floodplains with sparse tree cover, amniotes may move between patches of low vegetation, and burrows using cover when available, and crossing exposed surfaces during cooler parts of the day or night. The spatial arrangement of cover elements, including shrubs, logs, and large stones, influences predator-prey interactions among amniotes themselves and between amniotes and larger predators, such as some amphibians and early synapsid carnivores present in these faunas. The presence of amniotes in late Carboniferous landscapes also has implications for the processing of terrestrial primary production. Herbivory among amniotes in this interval appears limited, with most taxa interpreted as carnivores or insectivores based on tooth form and jaw mechanics, so their direct impact on living plant biomass is probably small compared with that of invertebrate herbivores. However, by consuming invertebrate detritivories and other small animals that feed on litter and fungi, amniotes form part of multi-step food chains that influence the rates and pathways of nutrient recycling in soils and on forest floors. Their feces and carcasses provide additional inputs of nitrogen and phosphorus-rich material to the detrital pool, which microbes and invertebrates then process. In the late Carboniferous interval, described here, early amniotes interact with vegetation, invertebrate soils and microclimates from the moist edges of coal swamps to the more open and periodically dry uplands and basin margins nearby. In the Coal Age lowlands described in earlier sections, peat accumulates on the floors of equatorial basins as successive generations of plants grow die and are preserved under waterlogged oxygen-poor conditions. At the time of formation, these peat bodies can reach thicknesses of several meters to several tens of meters, in places depending on how long mire conditions persist at a given surface, before they are disrupted by flooding clastic influx or changes in water table position. The peat is not a uniform mass. It contains recognizable root stems, leaves and spores, along with fine amorphous organic material and small amounts of mineral sediment carried in by rivers or wind. Its water content is high, with much of the pore space between plant fragments filled by water and dissolved gases. When subsidence of the basin and regional sea level change bring new sediment loads across the landscape, these peat bodies are buried beneath layers of mud, silt and sand. In many Carboniferous cyclothems, a coal seam lies above a rooted paleosol or seat earth, and below a package of fine-grained shale or sandstone interpreted as floodplain estuarine or shallow marine deposits, recording a transition from subaerial mire to clastic burial as base level rises and the depositional system shifts. As overlying sediments accumulate, the weight of the column above the peat increases. The peat responds by compacting. Water is expelled upward and laterally through its pore network, and plant fragments are pressed closer together. Petrographic and stratigraphic comparisons between estimated original peat volumes and present coal thicknesses indicate that compaction can reduce thickness to less than 1/5, and in some cases to about 1/10 of the original peat, although the exact ratio depends on initial porosity ash content and the timing of burial relative to decomposition. During this mechanical stage, the main changes are physical, but chemical alteration begins as well. With increasing burial depth, the peat experiences higher temperatures according to the local geothermal gradient, which in many basins is on the order of a few tens of degrees Celsius per kilometre. At depths of 1 kilometre and more, temperatures and pressures are sufficient to drive off some of the more volatile components of the organic matter, including water, carbon dioxide and light hydrocarbons, and to reorganize the remaining macromolecular structure toward more carbon-rich compositions. The process of progressive chemical and physical alteration under these conditions is termed coalification. Along the coalification pathway, peat first passes into brown coal or lignite, in which plant structures are still relatively easy to recognize at hand. Specimen scale, but moisture and oxygen contents are lower and carbon content higher than in unburied peat. With further burial and heating, the material transforms into subbituminous and then bituminous coal. In many Carboniferous provinces, including Euramerica and parts of Asia, the majority of seams that have remained in place since late Paleozoic burial reach bituminous rank with variations in volatile content that reflect different maximum temperatures and durations of heating. In regions affected by later tectonic thickening contact metamorphism or elevated heat flow, some Carboniferous coals advance further along this path towards semi-anthracite and anthracite, while in areas with more modest burial histories they may remain at lower ranks. At the microscopic scale, coalification reorganizes the plant-derived organic matter into Mackerel's petrographic components that can be distinguished under reflected light. Vitrinite, derived primarily from woody tissues and certain cell wall materials, becomes increasingly reflective and carbon-rich with rank, and often dominates Carboniferous bituminous coals in many basins. Inertinite, formed from strongly oxidized or charred plant material and from tissues exposed to drying or surface fires before burial, also contributes substantial proportions, especially in seams deposited in raised mires and in settings where wildfires or subaerial oxidation affected plant debris prior to final incorporation into the peat. Liptinite, derived from spores, resins, waxes, and other hydrogen-rich components, tends to be present in smaller proportions, but plays an important role in hydrocarbon generation at appropriate maturities. Together, these macerables record both the original biological inputs and the subsequent coalification conditions. As burial proceeds, fluids circulating through the peat and its enclosing sediments transport dissolved ions and gases. Early diagenetic processes in waterlogged sulfate-bearing environments can precipitate pyrite within the peat and adjacent mudstones, while carbonate cements form where pore waters become supersaturated with respect to calcite or siderite, often in association with microbial modification of dissolved carbon species. Fine clays, quartz silt, and other detrital minerals infiltrate fractures and pore spaces within the peat, during and shortly after burial, increasing the ash content of parts of the seam. Over time, compaction of the peat and differential compaction between coal and its surrounding clastic units influence the geometry of the seam and associated strata. Coal, being more compressible than most sandstones and many mudstones, tends to compact more strongly under the same overburden. In multi-cycle successions, this differential compaction can cause overlying beds to drape over coal bodies, producing minor flexures and influencing fracture patterns in roof and floor strata. In underground exposures and drill cores, seat earths beneath coals often preserve root traces and soil structures overprinted by compaction, while roof shales and siltstones show evidence of loading and dewatering features associated with the collapse of peat surfaces and the influx of sediment-laden water during flooding events that mark the end of peat accumulation. The thermal evolution of Carboniferous coal seams continues as long as burial depth and heat flow increase, and coalification advances to the highest rank corresponding to the maximum temperature reached. Once strata begin to uplift and cool during later tectonic phases, coal rank no longer increases because the reactions involved are largely irreversible under decreasing temperature and pressure. In thick accumulations of late Paleozoic sedimentary rocks, such as those in parts of the Appalachian Donets and Chinshui basins, reconstructions of burial and thermal histories show that Carboniferous coals pass through windows of temperature suitable for generation of thermogenic methane and other hydrocarbons which migrated within and away from the seams depending on permeability and structural configuration. In shallower parts of these basins where coal remained at lower rank and groundwater is still present, microbial processes continue to produce methane at low rates today, using residual organic substrates within the coal and associated sediments. In a cross-section through a mature Carboniferous basin, the vertical arrangement of coal and related rocks thus reflects many stages of this history. At the surface, modern erosion may expose weathered coal seams and associated seat earths with plant fossils and soil features still visible. At shallow depths, lignite to high, volatile bituminous coal may show relatively low reflectance and retain more original tissue structure. At greater depths, medium and low volatile bituminous coal and locally anthracite are harder, more lustrous, and characterized by higher vitrinite reflectance values, indicating higher maximum temperatures. Around and between the seams, stacked packages of sandstone, siltstone, shale, and occasional limestone preserve the fluvial, deltic, and shallow marine environments that alternated with peat-forming mires through Carboniferous time, while the coal beds themselves represent those intervals when peat not only formed, but was buried and retained under conditions conducive to its transformation into the compact carbon-rich layers that record the long-term fate of the swamp forests described in earlier sections. In the Carboniferous Earth system, the behavior of carbon and oxygen is governed by exchanges between atmosphere, oceans, biosphere, and sediments, with peat-forming wetlands and their burial playing a distinctive role in shifting the balance of gases in the air. At the global scale, the long-term carbon cycle links volcanic and metamorphic outgassing of carbon dioxide, weathering of silicate and carbonate rocks, productivity of marine and terrestrial ecosystems, and burial of organic matter and carbonate minerals. In steady conditions, inputs and outputs of carbon roughly match, so that atmospheric carbon dioxide and oxygen vary only slowly, but during the Carboniferous, the establishment of large long-lived peatlands on land, and their repeated burial as coal seams increase the net flux of organic carbon into sediments. Geochemical reconstructions that combine models with proxy data indicate that over intervals of tens of millions of years in the later Paleozoic organic carbon burial rates reach some of the highest values of the last 500 million years, coinciding with widespread formation of coal from tropical peat mires. At the same time, the drawdown of carbon dioxide by weathering of silicate rocks and by organic burial reduces the partial pressure of this greenhouse gas, while the release of oxygen during photosynthesis and its partial retention in buried organic matter raises atmospheric oxygen above modern values during significant parts of the Carboniferous. Estimates vary between models, but many converge on a picture in which oxygen concentrations rise well above 1/5 of the atmosphere and may approach or exceed roughly 1/4 to 1/3, while carbon dioxide remains low compared with many other intervals. Within this framework, peat-forming basins act as spatially local but globally important sites, where carbon is taken up by plants stored in waterlogged substrates that limit oxidation and then transferred into deeper parts of the sedimentary system. Each mire is a local expression of global mass balance equations, and the cumulative effect of many such mires operating over millions of years produces the atmospheric pattern inferred from proxies. The long-term consequences of this shift in gas composition include cooler mean temperatures supported by low carbon dioxide and a greater capacity of the atmosphere to sustain combustion due to higher oxygen. In the same interval, the fossil record documents that wildfire is a persistent and sometimes frequent process in vegetated landscapes. Charcoalified plant fragments and macroscopic charcoal occur in a wide range of Carboniferous sediments, including coals, seat earths, roof shales, and some marine units that receive debris from land. In coal petrography, much of this fossil charcoal is classified as inertinate, a group of mackerels with high reflectance and distinctive cellular textures that record charring of plant tissues at elevated temperatures. Surveys of coal from multiple basins show that inertinite proportions rise from low values in earlier Paleozoic deposits to much higher average values in Carboniferous and Permian seams, consistent with repeated exposure of vegetation and peat surfaces to fire under oxygen-rich conditions. Experimental work on the relationship between atmospheric oxygen and fire behavior supports the idea that once oxygen passes a threshold, somewhat above modern levels, wildfires ignite, more readily spread more easily, and can burn wetter fuels than at lower oxygen. In a Carboniferous peat basin, the interaction between fire hydrology and vegetation therefore depends on both local moisture conditions and the elevated oxygen content of the atmosphere. Under very wet, ever-saturated conditions, live peat surface layers resist burning, except during unusual dry spells, or when stand structure allows sufficient drying of litter and canopy material. Along basin margins, levees and better drained hummocks, litter layers and deadwood can dry enough between rainfall events to sustain surface and ground fires, which char standing trunks, fallen stems and litter, without necessarily consuming the deeper waterlogged peat. Evidence from inertinite textures in Carboniferous coals suggests a range of fire types from low-intensity ground and surface fires that char woody tissues at relatively moderate temperatures to more intense events that generate highly reflective charcoal indicating higher temperature regimes. Within the broader carbon cycle, these fires release part of the previously fixed carbon back to the atmosphere as carbon dioxide and other gases, while a fraction remains behind as charcoal that is more resistant to decay than unburned plant material. That charcoal, once incorporated into peat and buried, represents a particularly stable form of organic carbon that can persist for long periods in sediments. Thus, fire both opposes and reinforces long-term carbon sequestration. It accelerates oxidation of some biomass, but converts another fraction into a refractory pool that locks up carbon more effectively when subsequently buried. At the scale of individual peatlands and coal seams, the imprint of these processes is visible in vertical and lateral variations in coal composition. Layers rich in inertinate alternate with layers richer in vitrinite derived from uncharred woody tissues and jellified plant matter, and the proportions of these components reflect the frequency and intensity of fires that affected the mire surface or nearby vegetation during the time of peat accumulation. Some seams show discrete inertinite-rich bands that likely record single or a few fire episodes, whereas others include more diffuse distributions of charcoal fragments mixed with other macerals, indicating more frequent or spatially variable burning. Between coal seams, paleosols and clastic units may contain charcoal laminae and dispersed fragments, recording fires in upland or floodplain settings whose products wash into basins and mix with other sediments. In the microenvironment of a Carboniferous peat carbon is partitioned between several forms. Living plants maintain structural carbon in tissues above and below ground. Recently, dead litter and fine roots accumulate near the surface where microbial activity under oxygen. Poor conditions proceed slowly converting some material into dissolved organic carbon that moves through pore waters and some into partially decomposed solids. Charred particles introduced by fire form an additional solid phase that resists biochemical attack. Pore waters carry dissolved inorganic carbon produced by microbial respiration which can be exchanged with overlying waters or precipitated as carbonate minerals where conditions permit. As burial progresses, compaction expels pore waters and collapses voids, bringing plant fragments, charcoal and mineral grains into closer contact. At depths, where temperatures rise, sufficiently chemical reactions reorganize organic molecules into the macromolecular structures characteristic of coal and the relative proportions of charcoal-derived inertinate and other mackerels continue to track the imprint of surface processes long after the original mire is gone. Within this evolving matrix, microscopic pores in charcoal fragments and vitrinite bands host residual fluids and gases, including methane generated thermogenically or by microbial activity at different stages of burial. Local gradients in pressure and composition drive slow diffusion of these species through the coal and into adjacent rocks. Over geological timescales, such fluxes are small compared with the original flux of carbon into the peat, but they demonstrate that even long after burial, the carbon in Carboniferous deposits remains part of a connected system of reservoirs and transfers. In the interval considered here, however, the dominant features of the carbon and oxygen cycles are the presence of extensive tropical peatlands that accumulate and bury large amounts of organic matter, high atmospheric oxygen that supports regular wildfire activity, with the production of resistant charcoal and ongoing weathering and sedimentary processes that together determine how much carbon remains as living tissue and peat in the near-surface environment, and how much enters deeper, more stable reservoirs as coal and associated organic rich rocks.